Alright, so we got about 3 minutes before the class starts. So I gotta show you this little thing that I bought the other day. Yeah, I really should not be promoting people to buy unnecessary, useless stuff, but this is one of those things that that I gotta have because of my occupation. So this is what it looks like. And it has got 4 buttons. The first button is applause. I don't think I'll ever use that one. The second one is crickets, which is probably the most frequently used button. The third one is rimshot. I might use that occasionally. And then the last one is boo, which is probably appropriate, at many points of this particular class. No, I'm not booing you. I'm kind of boo myself. So yeah, every time I make a stupid mistake, it's gonna be yeah, that's gonna be a yes. As I said, I really should not be wasting my money to buy something that is totally useless. But I couldn't resist. I could not resist. So the crickets is actually pretty good too. Here, this is what it sounds like. Yeah, I think that's pretty cool. I tried my best, to find a way to do it electronically, on the computer, and that turned out to be not that easy. Controlling, because I have to make virtual audio, channels, syncs in order to attempt to get it to work. So it's actually a whole lot easier just to get a device externally. My phone can do it too, but I don't want to, use my phone, for this purpose. My phone has other purposes to serve. So this one is just for making those stupid sounds. And of course, having a maybe at some point I'll look into it again, but I think it would be kind of funny to have a tumbleweed being blown across the screen. That would be kind of funny too. The homework answer? We'll get to that. I cannot remember. Some of you can disclose the answer here. I mean, it's not like people who have not turned it in would have enough time to copy your answer. So you can go ahead and post your answer in the text channel. I don't mind. I mean, some people may be able to copy just the answer, but without the steps, that would be a 0 right there. So, okay. Alright, so it depends on where you got stuck. Okay, there's always a place to get unstuck. So maybe I really should not be doing it myself. Maybe I would have you guys to kind of put out your solution in the text channel, and then I'll copy that to my tablet, and then we can work it out from there. I think that's probably more helpful that way. Oh no, not handwritten stuff. No, no. Penmanship. Because when someone is... Oh, okay, there we go. Okay, so Jonathan has a... Okay, so Jonathan worked it all the way down to the solution. Okay. Yes, Discord. So one way to get around that problem of Discord getting rid of the asterisk, which really should not be there, because is to exactly. So Jonathan knew how to escape it. Basically it's backquote, 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 and then followed by the text, and then end it with backquote, backquote, backquote. So that would turn everything into just literal, because that's supposed to be program code mode, which is the same thing as a pre-formatted HTML thingy. There we go. So on, just learn really quickly. Very good. Excellent. So she got the answers, right? I mean, that's the right answer. Okay. Alright, so it's time to get started. I'm not really sure, who has a Okay, so I guess we can do it with Tosh example here. All right, so let me copy it into the tablet and then we'll work from there. All right, so I'm going to copy Tosh's answer into the tablet and then we'll start with that one. All right, so now I'm not sure whether that is the answer or not, but I'm going to give it a try. So it's P or Q and not R. So I'm going to use the shorthand, not the longhand method, or not Q, or not S and T. There we go. All right. All right. So so Tosh, you might want to make sure that I copied from your last expression correctly. I think I did, but I just want to double check and make sure. So I'm actually scanning between the two windows to make sure that I copied everything correctly. Okay, so that looks right to me, and obviously I'm using the shorthand, so that means there's no need to use the and t here, so it's just not S and T like that. Okay, looks right. Good, very good. All right, so at this point, we want to turn it into a gigantic conjunction where each item in the conjunction is a disjunction. So the way we do the conversion is to use distribution. So distribution is what we can use in this case. Let's see. There should be something indicating this asterisk before the not R. That's an and. So we don't use a symbol because we just look at whatever we use to denote multiplication is what we use to denote conjunction in this class in the shorthand. So that's why there's no need to do it. All right. Okay. So let's go ahead and work this out. So we need to get rid of all the nesting, right? Because that's the whole point is to get rid of all the nesting unless we end up with a gigantic conjunction and every term is a disjunction of only variables or the negation of variables. So we are definitely not quite there yet. All right, so the first thing we do is we apply distribution here. So that becomes P and not R. And once again, I'm a little bit inconsistent because negation is exclamation point. But when I'm handwriting, exclamation point is actually, it takes longer to write it compared to the negation symbol. So when I'm handwriting, I'm going to use the actual negation symbol because it's a little bit faster to write it. And then we have an OR. Then we have Q, not R. And then we have an OR, so we can dissolve this pair of parentheses because disjunction is associative. So that's why we can get rid of all the parentheses. So this not Q is all by itself, and then we have that last OR thing, which is not S and T. Are we doing okay so far with this? I just used the distribution on the first term. That's all I did. So it would appear that we are now completely stuck because now instead of a C and F, which is conjunctive normal form, now we have a disjunctive normal form, a D and F, which is not what we want, okay? So how are we going to fix this problem? Well, we're going to use distribution in order to turn this into one gigantic conjunction of disjunctions. That is what we're going to do. So instead of using one single step to do it, I'm going to break it up into smaller steps. So what I'll do is I'm going to take care of the first disjunction first. So I'm going to take care of this one first. Let's see. All right, so let's quote the rule, of what distribution we are talking about. So we are talking about the distribution of A, B, A and B or C is the same thing as A or C and B or C. So this is the distribution that's gonna get us out of this hole. Alright, try to get rid of the Q's. Okay. Alright, so in this case we have basically this it's I'm trying to look for the word foil. Okay, this is foil because we have 4 terms, and basically we're going to reverse back to what we had earlier, which is P or Q, the whole thing, and R. And now we try to lump one more term and then leave the other one alone, just like outside. So now we have this particular expression is matching this pattern here. So what we're going to do is going to do the same thing. So in this case we have we take the first one, which is P or Q, and then we have the or not Q over here, and then the whole thing is ended with not R or not Q. And then we leave the other one alone because we are not quite there yet to process it. So I want to make sure that this is okay so far. I want everybody to be able to see how P or Q is matching the placeholder of A, not R is matching the placeholder of B, and then not Q is matching the placeholder of C. So when you look at those placeholders, okay, A, B, and C are basically placeholders. So once we substitute P or Q into A, not R into B, and then not Q into C, we now you'll see this particular pattern. We can apply distribution, and then after we apply distribution, we end up with this particular end result. Does that work? So yeah, the second step is redundant. Yes. So this step here is completely redundant, but it really kind of shows that we can start with something that looks that ugly, and be able to gradually turn it into a CNF. There we go. This is no. We are not applying resolution whatsoever. There's no resolution whatsoever here. This is just distribution. That's all it is. No, this is just distribution. That's all. It's this part here is distribution. It's one of the distribution rules that I have mentioned in the previous class. No, you're not dumb. Maybe you just forgot that we have distribution like that, because this is not there's no equivalence of this distribution in normal algebra. That's all. All right, so let's move on. Yeah, absolutely. So now we're going to take a look at the distribution again, and see whether we can apply distribution again. So it looks like we can, because now we have let's see, we can actually apply FOIL this time. This is basically FOIL, but instead of using FOIL, which is doing basically two distribution steps in one single step. So instead of doing that, we're going to do this in a more conventional way. So we'll apply distribution just one step at a time. So this time we can see how P or Q or not Q. Now, if you want to save yourself a lot of trouble, you simplify first, okay? Because in the example in the notes, I did not simplify first, and that's how we ended up with an expression that requires a little bit of panning to see the entire thing. So I'm going to apply some simplification here, because Q or not Q is basically true. Now this is, I'm really applying simplification one step at a time here. So now we have P or Q, P or true. Anything or true is just true. That's one of the simplification rules. So we have true and not R or not Q or not S and T. But true and whatever is just whatever. So we simplify again. So now we just end up with not R or not Q, or not S and T. Are we doing okay so far? All right, cool. Yes, so Jonathan is correct in the text channel that we should simplify the Q or not Q first, because that just knocked one ugly looking term completely out. Okay, so the whole thing looks a little bit simpler now. All right, so now we still have something or something or something, and then the last something here is a conjunction. So that means we still do not have a CNF. So the question is, what are we going to do with this? So what we're going to do with this is to let's see. We can apply distribution again. I mean, we really don't have a choice, except to apply distribution. So there are two distribution rules. The other distribution rule is A or B and C becomes A and C or B and C, which looks exactly like the algebra distribution rule that you are familiar with. So that one doesn't seem applicable either. Oh, I know. Okay, we're still going to apply the first one. We're still going to apply the first one because A is not S, B is our T, and then C is the entire thing of not R or not Q. There we go. So we can just do that. Is everybody clear on what we are planning to do? The placeholder, which one is which one? Okay, Jonathan is okay with that. Douglas is okay with that. Okay, so I just didn't see it because the order was reversed. Okay, but that's okay. So now we apply the distribution. So once again, this part here, this entire part is our C, and then not S is our A, T is our B. So once we apply distribution, then we will end up with A and C. So we'll end up with A or C, sorry. So it's A or C. So now we end up with not R or not Q or not S as one, and then we have the conjunction with the other one, which is not R or not Q or not this is not negated, or T, and now we have the final solution because now it is in CNF. Yep, one of the very rare occasions where it is appropriate. So the question is distribution versus FOIL. FOIL is distribution. So FOIL is distribution applied twice in one single step, but it is just distribution. Let's see. Oh, look, sounds like a vacuum cleaner. I wish my vacuum cleaner sounds like that. It doesn't. Then Boolean laws are confusing. It's confusing only because it's new to us. But when you look at the list of all the applicable Boolean algebra rules, they're just rules. I mean, all you have to do is to look at all the alternatives and find out, okay, which one should I apply. So it is its own kind of algebra. Boolean algebra is an algebra. It's just that it has different rules compared to the algebra that you are used to. All right. Nah, this is not calculus. Yep. I think I mentioned already, there's a class in most four-year universities called abstract algebra. So it's not algebra, it's not linear algebra, it's not Boolean algebra, it is called abstract algebra. And that is what is equivalent to our CISP440 in the computer science program. It's a divide class. Basically, people who pass that class can continue on to become a math major, but a significant number of people cannot pass that particular class, and that basically means they cannot continue as a math major, because abstract algebra, as the name implies, involves a lot of abstraction, And abstraction really is the name of the game when it comes to mathematics. But when you think about it, programming or computer science is really a branch of mathematics, which also means in programming, we actually have to use abstraction a lot as well. I mean, the whole point of writing a program is an abstraction. Instead of actually performing the steps individually, and do it differently for every single problem, we are trying to abstract into steps where those steps can be applied to many different instances of problems as long as the problems fit into a particular pattern. And the whole word, the word pattern implies abstraction. So there you go. All right, so we got the answer to this one, and I think we are ready to continue to the new topic. Okay, so we're getting back to counting. And the counting module is right here. I just put it up already right before class. And we're going to start from the beginning because we need to excuse me, we got to make sure that we got the terms right, okay? Because otherwise, it's difficult to explain one concept with using other concepts. All right, so we got on typing. All right. Yeah, we just got a new assignment. The new assignment is a continuation of the CNF assignment. So this time I give you two proposed theorems, and you have to prove whether those theorems are in fact theorems or not, using resolution and also proof by contradiction, and only using those. So you cannot use algebra this time to prove the theorems. You have to use resolution and also proof by contradiction to prove the theorems, or to show that it is not a theorem. So there we go. You have 1 week to work on that one too, so that's plenty of time to work on that one. Okay. All right. So getting back to the terms here. So the first term that I want to explain is the term trial. So a trial is a single attempt to do something, typically involving choosing something. A single choice is a trial. Okay, so let me give you some examples of what a trial is. Flipping a coin is a trial. Okay, it is a single action that has ends up with some possible outcomes. Throwing a dice once is a trial. Drawing a numbered ball, for the lotto game, is a single trial. So basically, a trial is basically just an action that ends up with a result, and that single result comes from a set of certain possibilities, certain possible outcomes. So that's what a trial is. And then the next paragraph explains that a trial has a set of possible outcomes associated with it. Each outcome represents a possible result of the trial. So let's go back to the examples that we have talked about. Okay, when you flip a coin, then the possible outcomes will be head or tail. Or head, tail becomes the two elements of the set of possible outcomes. If you throw a dice, and we are assuming this is a cubic kind of dice, then you have 6 elements in the set of outcomes, because you can have 1, 2, 3, 4, 5, 6 as the possible outcomes. If you are talking about lottery, okay, when we are drawing the first number out of the entire big basket of numbers, then you have 47 possible outcomes, because because when you draw the first number, no number has been drawn before, so all 47 numbers are possible outcomes, and as a result, they all become a part of the set of the possible outcomes. So are these two paragraphs okay? I mean, just the concept of a trial and the set of possible outcomes associated with a particular trial. Okay, so we got one confirmation. And we got Jonathan Camarina typing. So I'll wait until that typing is done before we move on. not seeing anything yet in the text channel. I'll keep an eye on the text channel, but I'm gonna move on to the concept of an experiment. Oh, there we go, we got it. So in my submission, I got a different answer, but it's still in CNF. It's possible. Jonathan Camarina is talking about the assignment. It is possible that it may not have been simplified entirely, so you might end up with more terms. It's okay. It's not wrong as long as it really is in CNF, and you just have some duplicate items that do not need to be there. Because I did not ask for the simplest CNF, so as long as it is still correct, I'll give you full points for that. All right. So moving on to more terms. An experiment is a series, okay? So the key term here is a series, okay? Where ordering is important. It's a series of trials where subsequent trials may be affected by earlier ones, and that means the possible outcomes may be affected. An experiment has its own outcomes. All right, so this part does require a little bit of explanation. And the best way to explain this is really to look at it from the tree perspective. So I'm going to go back to the tablet in order to show you what it looks like as a tree. Okay. So let's first think about tossing a coin. Okay. So when you start, you're at the root of a tree. The first toss gives you two possible outcomes. So you can have head or tail after the first toss. But after the first toss, when you're performing the second toss, if the first toss was a head, guess what? The second toss would also give you the possibility of having another head, or this time it might be a tail. If the first toss ends up with a tail, then the second toss can also be a head or a tail. Okay? So this is basically just a binary tree. Every time you have another trial in the experiment, you have basically you're increasing the level of the tree by 1. So the next level is going to end up with 8 leaves, okay, 8 nodes at the very end. So when we talk about the outcome for the entire experiment, this is what we are talking about. Okay, we are talking about head, 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 tail, tail, head, and tail, tail. This is the set of outcomes for the experiment, and this particular experiment involves 2 trials. Are we doing okay so far with those terms? And this one is using tossing a coin as an example. Okay, good. Excellent. All right, so we'll take a look at another example. Okay, so Jonathan says, so experiment outcome is dependent on earlier trials. It depends on all the trials, because you're looking at the outcome of each trial and then form a tuple for as the outcome of the entire experiment. And then Armand is typing subsequent trials aren't affected by earlier trials. In this specific case, that is true. And that's why I'm going to give you a second example where the second trial is affected by the first trial in terms of what outcomes are possible in that case. All right. Yes, so we are talking about the elements of the set of possible outcome. It can be affected by an earlier trial. So in this case, okay, the best way to visualize it is you have a bag, and in the bag you have 3 marbles. One is labeled 1, one is labeled 2, and one is labeled 3. So you got 3 marbles in a bag, and then each trial is to draw 1 marble out of the bag, but not to put it back in. Okay, once you select a marble out of the bag and take it out, you're not going to put it back. So in this case, the first trial has 3 possibilities. You can have a marble labeled 1, one that's labeled 2, or one that is labeled 3. However, when you look at the second trial, now it depends, because if the first trial is taking the marble labeled 1 out of it, then in the second trial you only got a 2 or a 3 as your possible outcomes. If in the first trial you have a 2, then the second trial can only have a 1 or a 3. If the first trial is taking the one number labeled 3 out of the bag, then you can only have the one labeled 1 or the one labeled 2 as possible outcomes of the second trial. So in this case, okay, when your experiment involves 2 trials, then the set of outcomes for the entire experiment of 2 trials is going to be 1 2, 1 3, 2 1, 2 3, 3 1, and 3 2. So this is now the set of possible outcomes for this particular experiment with 2 trials. Are we doing okay so far with this explanation? And I think visualizing the whole thing as a tree really helps. Now, it only works when you have simple examples like this. Okay, when you have complicated things like 50 people in the class and we have 365 days to choose from, guess what? That is not appropriate to be represented graphically, because you can, conceptually it is no different from something like this. However, it is just going to be, the first trial is going to have 365 possible outcomes. It's just way too tedious to represent it graphically. But when you only have 3 marbles in a bag, hey, it's not too bad. So this is a trick, this is a technique to help understand concepts, is not to start with something that is complicated. Start with something that is almost trivial, okay, and then use that as an example so that you can kind of run through, so if I have this kind of situation, this kind of experiment and this number of trials, I can actually visualize the entire experiment and be able to tell at the very end of the experiment what kind of outcomes as a sequence, as a tuple, can I possibly end up with. So that's a trick, okay? It's a very important trick to understand complex concepts, is to try to use simple examples that are still, legitimate examples of the concept that you're trying to learn, but nonetheless, make the examples as simple as possible. Alright, so we have now talked about experiments, and in general, the outcome of an experiment is represented by the symbol omega. So omega in this context is no longer the set of all the operators, or otherwise known as connectives. Omega in this case is now the set of outcomes. Alright, so moving on. So if all you're interested in is counting, then this particular section handles all the counting with replacement. So we are talking about tossing a coin or throwing a dice. The next one without replacement is the one where you draw something out of a bag but you don't put it back in, so the item that you have taken out is no longer an option for further trials. So we are separating it into 2 cases. The first one is just with replacement. So if you toss a coin the first time, it lands on the head. The second time it can still land on the head. So that is called with replacement. Okay, because basically all the trials have exactly the same set of outcomes, which makes the analysis very simple to deal with. So here we have some notations, so we'll start with notations. Let Ti represent the outcome set of trial I, where I is 0 oriented. So most things that we talk about in this class are going to be 0 oriented, because C and C++ and all programming languages have array indexes being 0 oriented. In the case where Ti does not influence Tj, where j is greater than I, the outcome of an experiment of n trials is going to be just the Cartesian product. It's easy because every single one of these t's is the same. So T0, T1, T2, all the way up to Tm minus 1, because we have m trials. Each one of these t's actually is exactly the same thing. So Cartesian product is used because every e in T0 as the first actual outcome from the first trial, every f is an element of T1 can be the outcome of the second trials, and so on. So that's why we use Cartesian product. But the way you can visualize why we use Cartesian product is even easier, okay? Because I didn't really quite incorporate graphical representation into the text, because it's just a lot of work to draw those pictures and put it into the text. But during the lecture, I give you something like this. Not this one, the previous one. There we go. There we go. So this is why it is a Cartesian product, because when we add one more trial, we are just appending to the leaves of the previous trial and go like, okay, this one has two possible outcome, when we want to look at the third trial. So this one has two, this one has two, this one has two, and this one has two. So now we end up with 8 possible outcomes for 3 trials, okay, for the experiment that has 3 trials. So I hope this helps to kind of visualize why we use Cartesian product in this case. All right. All right, cool. Yeah, ordering does matter, okay? So up to this point, we are going to assume ordering does matter for everything. Because once you understand how to do all the counting, when ordering is important, it's very easy to take into consideration that, oh, by the way, ordering is not important. We actually demonstrated that when we talk about the lotto problem in the previous class, but we'll get to that point again. All right, and for counting purposes, the outcome space has a cardinality of, so when I use big pi, this is the pi symbol, it means the product of these terms. So I as a variable is going to go from 0 to m minus 1, and then each term is the cardinality of ti, and we just have to multiply the cardinality of t0 to the cardinality of t1 times all the way up to the cardinality of t subscript m minus 1, and that gigantic product is the cardinality of the outcome space for the entire experiment of m trials. And I can see that someone, Armand, is typing in the text channel, but I'm gonna finish up this last paragraph, and then I'll wait for the text to come in. In some cases, the set of outcomes are the same for all trials. In all cases, okay, in all cases where each trial involves the same kind of action. So in that case, t0, t1, all the way up to tm minus 1 is really just a particular set of t. And if we assume the cardinality of t is n, then the cardinality of the entire experiment of m trials is simplified to n to the power of m. There we go. And we have seen this already, by the way. We have seen this when we talked about the birthday problem, when we're trying to figure out, if we don't have any restrictions, how many possible ways do we have to arrange birthdays to m people, and n in that case is going to be 365 because there are 365 days in a year. Oh, okay. Okay, let me explain that using the tablet because it's easier to kind of just write out what it means. Okay, so the big pi symbol it's the same thing as sigma, except we are not adding, we are multiplying. That's basically the difference. So if I just go from 0 to some n over here, and this is f of I, which makes it kind of really general because we can just say, okay, whatever f of I returns, right? So this becomes f of 0 times f of 1 times f of 2 times blah 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 all the way up to f of n. That's basically what the pi symbol is doing, because what sigma does is it is adding all of the terms, and what pi does is to multiply all the terms. And the reason why they use big pi is, okay, so sigma is about the same as s in English, in the English alphabet, and s is for sum. So big pi is about the same thing as p, which is for product. So that's why, big pi is for a product, a long product of terms, and then the sigma, on the other hand, is for sum. Or at least that's how I remember these symbols. And cardinality is a natural number, and as a result, yes, they can be multiplied. Yep, yep. So those are all correct. Cool. And let's move on. Okay, so when the trials of an experiment are with replacement, which means earlier trials do not impact the possible outcomes of later trials, then it's pretty easy to figure things out because you're just looking at the power of something. So now the question is, what if it is without replacement? In other words, once you take something out to become the outcome, the actual outcome of a particular trial, that thing it's not available anymore. So now, in terms of what we are working on earlier, it is this particular scenario. Okay, yeah, there's a little lag time between when I talk and when the tablet decides to refresh on the screen that you can see. So in this case, it is without replacement because because once we take the marble labeled 1 out of the bag, it is no longer available to trial 1. This is trial 0, this is trial 1. So you can kind of imagine if we expand it one more time, then this one has no choice whatsoever. It has to have just the marble labeled 3, and this one only has the marble labeled 2. This one has to be 3, this one has to be 1, this one has to be 2, and this one has to be 1. So are we doing okay so far with the concept of without replacement? You take something out of a collection and it is no longer available for subsequent trials. Okay, very good. So now the question is, if I only care about counting, how are we going to do that? I mean, you can see this already because the first one, we start with the original number of items in the bag. And then the next one is that number minus 1. And then we have to subtract 2 from the original number when we come to the third trial. So if counting is all you care, then you're talking about something that looks like this. Okay, so for without replacement, and I'm going to use n to represent the cardinality of t0. So t0, remember, the subscript 0 means this is the outcome set of trial 0, which is the first trial. So let's just say that we keep taking things out of that set, okay? And we have m trials. So now, when you look at the cardinality of omega, which is the set of all the outcomes for the entire experiment of m trials, it is going to be the first one has n, the second one has n minus 1, and then we have n minus 2, all the way down to n minus m plus 1. Okay? So that becomes the number of possible experiment outcomes when you have n items to start with and you have m trials. Are we doing okay so far with this? Alright, very good. So now the question is, how do we express this, right? I mean, this looks pretty ugly. So one way to express this, okay, excuse me, I'm gonna have to there's some kind of allergen, I'm allergic to something in the air, so it's irritating my eyes. Alright, so we are looking for a better way to represent this, right? So the next way to do this is, we can use the big pi notation, where I is going from n minus m plus 1 all the way to n, and we just have to multiply each term, which is the index I itself. Yeah, that works too, but it still doesn't look very nice, okay? So now we're trying to use another way to look at this. If I just show you the first portion, n times n minus 1 times n minus 2 and so on, some people are thinking, factorial, this looks like factorial. Well, it is almost like factorial, except sometimes we stop short, right? Because sometimes we don't go all the way down to 1. So, but there's a way to deal with this. So let's just say that, as the numerator, we go all the way down to 1. So now we say, how do we get rid of the items that we don't need, okay? Because we only want the last item to multiply to be just n minus m plus 1. So now we just say, hey, if you divide it by this, okay, and that, and all the way up to n minus m, then we would have, quote-unquote, canceled out the items that we don't need. We will just have everything down to n minus m plus 1. So now when you look at the numerator, that is just n factorial. But when you look at the denominator, it is m factorial. So this is the final form. Okay? If you have an experiment where you have m trials, but you have n choices for the first trial, for trial 0, if you only want to know how many ways, okay, how many possible outcomes can I get out of the entire experiment, that's just n factorial divided by m factorial. And we even have a better shorthand to represent this. This is basically the permutation of n chooses m. So the p notation is, there are several variations of the p notation. Sometimes we put the numbers 1 in front and 1 after, and sometimes we put 1 on top and 1 below. And when you use a spreadsheet, okay, the spreadsheet called this permut. Okay, so instead of spelling out the entire permutation, they just spell out permute. Okay, and then you supply n and then m as the argument in order to calculate permutation using a spreadsheet. It's pretty handy, if you use a spreadsheet to do all this stuff. So do we have any questions about the counting part? Okay, if we only want to know how many ways, okay, and not really caring about exactly what ways we are talking about, we just want to know how many. This is how we do it. Okay, one is using power, and the other one is using basically a factorial divided by another factorial. Are we good so far? Okay, very good. And you can plug these equations back in to the earlier examples that we have talked about. Okay, so let's do exactly that. Okay, so in this case, okay, let me erase this part because now the tree is representing an experiment that is without replacement. We have 3 items to begin with because there are 3 marbles in the bag originally, and we have 3 trials because we are basically performing the steps 3 times. Take 1 marble out of the bag is 1 trial. Take 1 marble out of the bag is the 2nd trial. Take 1 marble out of the bag is the 3rd trial. Except in the 2nd trial, whatever you have taken out cannot be taken out again. So now, when you look at the cardinality of omega, remember earlier what we said? N is representing the number of items in trial 0. It is 3. And then m is representing the number of trials, which is also 3 in this case. So, wait, hold on a second. It is not that, right? It's n minus m factorial. There we go. I might have made a mistake in the... Yep, I made a mistake here. Sorry about that. This is n minus m factorial. That was my mistake. I apologize. Is that okay? Does it help? Maybe our mind is not understanding because I messed up my own math. And this would be a very appropriate time for this. Is that helping? Yeah. Okay. Very good. So, as I said, I made a mistake because I was staring at n minus m times, a whole bunch of numbers all the way down to 1. That is n minus m, the whole thing factorial, not m factorial. So I made that mistake. So, but I spot my own mistake because when I try to apply this in the picture, it doesn't work out. Oh, okay, my watch is buzzing. It's time for rotating. Kind of like a intermission entertainment thing, except it's not very entertaining. So there we go. I'll show you the answer. I mean, I can just type the answer. I know what the answer is. I can just type it in the text channel, but I'm going to show it. Okay, it's just outcome, but I'll type it in the text channel so you can just copy and paste it. There we go. And then we'll just go ahead and save and publish. There we go. So you have about 9 minutes to type the word outcome. I would just copy and paste. So if it doesn't work, you have me to blame. And then I get another chance to use the boo sound effect. Alright, so we got Armand typing. Can I take a look at the scratch from the tablet? Yes. So let's get back to the tablet here. Alright, so let's work out what is n and m in this case. N equals to 3 in this particular experiment because we got 3 items in the bag to begin with. M is also 3 because we got 3 trials. This is the first trial, this is the second trial, and this is the third trial. So that's why m is also 3. So when you look at the cardinality of omega, it becomes 3 factorial divided by 3 minus 3, the whole thing factorial, which is 3 factorial divided by 0 factorial. And in this case, it is not a division by 0 because 0 factorial is not 0. 0 factorial is 1. So that means we just get 6 because 3 factorial is 6. Well, does that make sense? Okay, so Armand said, oh, we are trying to find the total number of outcomes for a certain experiment with m trials. Yes, that's exactly what we were trying to figure out in section, I think, 5. Section 4. Okay, never mind. Section 4. And section 4 uses some notations here to kind of show, basically explaining exactly the same thing but using mathematical symbols. Alright, so I hope we are good up to this point with all the counting. In other words, if all we care is to find out how many ways can we blah 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 blah, we now have the more or less closed form equations to do it. Because factorial, still is not exactly closed. It's not a closed form, but it's close enough. All right. So I'm not seeing any questions, which means we're going to move on. So now we're talking about ordering. Okay. So what if ordering is not important? Because everything that we talked about earlier is based on the assumption that ordering is important. Let me go back to the tablet to show you what I mean by that. So in this particular case, if I draw the balls in the order of 1, 2, 3, it will be considered different from drawing the balls as 1, 3, 2. Okay, so the ordering is important in this case. So what if ordering is not important? How do we deal with the situation where ordering is not important? So what we do is an example. to basically say, well, if ordering is not important, then we have to find out, okay, how many, these are called permutations. So each outcome is called a permutation, where it is represented by a tuple, and each item in the tuple is representing the actual outcome of a particular trial. So if it is not important, if ordering is not important, the first thing we need to know is, okay, so if all I care is whether something is chosen or not, but I really don't care about in which trial it is taken out of the bag, what are we going to do? So we need to find a number of ways for a certain number of items to rearrange themselves. Okay, so let me give you another example, because this example is not useful for that discussion. So I'm going to have to use another one for that specific discussion. So in this case, we have a bag, and in the bag we have the numbers 1, 2, 3, and 4. I just lied. Let's change these so they're not numbers, because that makes it easier to actually visualize. So we have A, B, C, and D. So we got these 4 things in the bag. You can say this is a very small scoop of alphabet soup, where you have these letters in the alphabet soup. So now the question is, if you are to scoop up one letter from the soup in each trial, and we only have 2 trials, and ordering is important. Okay, let's assume ordering is important first. How many outcomes are we talking about? Now, this time it is actually kind of important not only to work out the number, because we know what the number is supposed to be. It is 4 divided by 4 minus 2, the whole thing factorial, which is 4 factorial divided by 2 factorial. 4 factorial is 4 times 3 times 2 times 1, which is 24. 2 factorial is 2 times 1, which is 2. So we end up with 12 possible outcomes when ordering is important. But this time, just knowing the cardinality is not enough, because we want to find out which 2 of these outcomes really belong to the same thing when ordering is not important. So we want to pick out all the quote-unquote duplicate items when ordering is no longer important. So we're going to do the tree thing again. Okay, so we have A, B, C, D in the first trial. So we got A, B, C, D. In the second trial, if A is chosen already, then I have 3 possible choices, right? Because we still have B, C, or D to choose from. But if I choose B first, then we have A, C, D left. If I choose C first, then we have A, B, D left. And if I chose D first, then we got A, B, C left. So in this very specific case, the actual outcome, the actual permutations are going to be AB, AC, AD, BA, BC, BD, CA, CB, CD, DA, DB, and then DC. Okay, so these are the actual 12 outcomes that we end up with when ordering is considered important. Then somebody's changing the rule and go like, I don't really care which one you get first, okay? As long as you end up with the letter A and the letter B, we are, that's considered equivalent, okay? I don't really care whether it's A, B, or BA. Ordering is not important. So now you're going to have to look for duplicates, right? So you look at this, okay, and you say, oh, this is a duplicate of BA. So these 2 are really kind of the same thing, okay? Yes, it's not a very technical term. If you want a technical term, I will say this, okay? These 2 permutations are corresponding to the same combination, because in a combination, ordering is not important, okay? Then you look at AC, and we say, oh, it's really the same thing as CA, okay? It's all the way down here. AD is the same as DA, which is all the way down here. And then BC is CB, which is here. BD and DB, okay, that's all the way down here. And then finally we have CD and DC, And there we go. Okay. So now you just have to count the number of combination. So we have 1, 2, 3, 4, 5, and 6. There are exactly 6 combinations when we have an experiment that has 4 as the cardinality of T0, and we have 2 trials. Okay. Are we still doing okay so far with this? And Armand is correct earlier. So we have to divide it by 2, exactly. Because in this case, we can find that, hey, there are, if I just focus, okay, if I just focus on A and B, I know there are exactly 2 ways to change the ordering so they appear to be different as permutations. And so we just have to divide it, right? So now we look at the permutation of NM, which is the number of permutations in an experiment. And then we just say, of all of these possible outcomes, m factorial of the permutations really belong to the same combination. So now we just have to divide it by m factorial. Does that make sense? We divide it by m factorial because if you focus on just m items, there are m factorial ways to reorder them. And since we say, ordering is not important, forget about ordering, then we basically now we are saying, for each combination that has m items, there are m factorial ways to arrange the permutations, and that's why we are dividing it, because we're combining every m factorial permutations into one single combination. So Armand asked, when order doesn't matter, the number of sets in omega decreases. The number of elements in omega decreases. Yes. So let's apply this back to an earlier example that we worked out. Okay. And that would be, come on, there we go. Okay, so it's going to be this tree here, okay? N is 3, M is also 3. So we have already figured out if ordering is important, then we have the permutation of 3 choose 3, and that turned out to be 6 in this case. But then if ordering is not important, we're going to have to divide it by 3 factorial, because in this case M is also 3. So you look at this and go like, it boils down to 1. Does that make sense, Jack? Are we making a mistake here? If ordering is not important, there's only one possible outcome if I choose 3 items out of 3 items from the bag. I mean, intuitively, does that make sense to you? Okay, we got some yeses. All right. Exactly, because you're basically emptying your bag, okay? And there's only one way to empty your bag when ordering is not important. So all the marbles you'll fall out of it, but you don't really care about how they fall out of the bag, because the idea is you just need everything to be out of the bag. There's only one way for everything to be out of the bag when ordering is no longer important. All right. So this is an interesting observation. So now we're going to look at some extreme examples. What if your bag is empty? And just so that everything is graphical, now I draw an empty bag. So with an empty bag, obviously you cannot have a single trial. Your number of trials has to be a 0. Okay, but we want to investigate. Okay, if we want to look at the number of permutations of how we can choose things out of a bag where ordering is important, that should still mean something, right? That should still mean something. So what are we getting in this case? In other words, what does this tree look like? This tree looks just like this. we have a single root node that is not representing anything. So First of all, what does omega look like in this case? Okay, we are looking at permutations in this case. So if ordering is important, what is the set of all the possible outcomes? I'm not looking at the count, okay? I want to look at the set itself, and then we can use the calculation to figure out whether they match or not, okay? So I want the exact, what is in the braces in this case. So because this is a boundary case, okay? So whenever you try to understand something, you have to exercise the boundary cases, especially when the boundary case is a simple one, okay? So in this case, what do you think is the item inside omega? Now, because you guys are so fast ahead of me to say that the cardinality is 1, that means this is not an empty set, right? If it's not an empty set, it has to have exactly one element in it, because the cardinality is exactly 1. So what is it? Jonathan is close. It is not an empty set, it is an empty tuple. Because when we are dealing with permutations, a permutation is represented by a tuple. So now we have a tuple that is empty, which is perfectly okay. This is an empty array. It is still an array. It's an array that has no elements. There we go. All right, so this is what happens when we have permutations. Now we try to look at it from the perspective of combination. Now, when we do combination, I just want to introduce the shorthand. So when we have n items and we choose m of them, sometimes the representation is n over m in parentheses. I'm not missing a bar. It is not a fraction. It is just n over m in parentheses. That is also a way to represent the number of combinations when you choose m out of n. In a spreadsheet, this is called combin for combination, and we supply n as the first argument and then supply m as the second argument. Okay, but the way it is defined is simply to make use of p and m, and the whole thing divided by m factorial. So when you plug in zeros for n and m, this is still a 1. Okay, I shouldn't say this, but C of 0, 0, which is 0, 0, which is combin 0, 0, is also 1. If you have an empty bag and I ask you how many ways can you take things out of it, using 0 steps, the answer is 1. So now the question is, when we look at combinations, when each outcome is a combination, what does omega look like in this case? We know there's one item in it because C of the if you apply the actual calculation to find out how many ways can we choose 0 item out of 0 item, it is 1. Okay, I can show the math in just a little bit, but it is 1, which means omega has one element in it. So the question is, what element are we talking about? And nope, this time it is not a set. So as it turns out, a combination is represented by a sorry, I misspoke. It is not an empty tuple, it is an empty set this time. Because we use a set to represent a combination. Because ordering is not important. It's very handy that, when we talk about the notation of a set, when we talk about the notion of a set, we already mentioned that, elements, the ordering of elements in a set does not matter. It's in terms of elements of a set, the only thing that matters is whether something is in the set or not in the set. There are no ordering within the elements of a set. So in this case, omega is basically a set of an empty set in it. Alright, so Aman is giving me a frowny face. And then Jonathan said set cannot have duplicates, but tuples can. Yes. And Jonathan also mentioned which is like permutation versus combination. Exactly. So when we think about permutation, we think of tuples. When we think of combinations, we think of sets. Now, let's go back and do the calculation, okay? Because we want to confirm that 0 choose 0, which is P of 0, 0, divided by 0 factorial, is indeed 1 divided by 1, which is exactly 1. So the math works out, okay, even in this really boundary case where you have nothing to begin with in the collection. Alrighty. So I'm just looking at the time. We got about 12 more minutes to go. Any questions at this point? We're still just doing the counting, but this time I'm using the more extreme and boundary cases just to make sure that we understand that the way we calculate permutations, the number of permutations and the number of combinations work in such boundary cases where there's nothing in the bag and you have 0 trials in an experiment and it still works out. It's very important that a particular theory, a particular way of looking at things also work out in all the boundary cases. Alright, so Jonathan said, is it possible to have more trials than the amount of things and there's no replacement? It's without replacement? The answer is no, you cannot. Yeah, you cannot. You simply cannot do that. There's no. It would be. I'm guessing it's going to be undefined. So you have to make sure that m is not greater than n when you have experiments that are without replacement. They can be the same, okay? N and m can be the same, but we have already seen what happens when they are exactly the same. I'm just waiting for questions to come in. So n choose m is just another way to write the combination of n choose m. Yeah, so nm, I have never seen the horizontal arrangement. I've only seen the vertical arrangement. So I'm not really sure whether the horizontal arrangement is also a accepted mathematical symbol. Okay. I just want to be sure. Okay, there we go. All right, so what we're going to do now is we're going to move on, and this time we are no longer talking about counting. This time we actually want to have a set of permutations, and also in section 7 we want to end up with a set of combinations. So now how are we going to do that? And if you have read this section, I don't know how many of you read this far ahead of the class, but if you have read this section, you'll notice that I am using a recursive definition here. So let me just point out, I'm skipping things, I'm jumping around a little bit here, because I want to start with the base case of the recursion, which is omega 0 of t is defined to be the set of an empty tuple. And then I use the recursive definition down here, which is omega of I of t is the union of the Cartesian product between a set that only has e in it and omega I minus 1. So the key here is it is recursive because omega I depends on omega I minus 1. And it is the same thing with section 7. So if you go on to section 7, I cannot use omega again because omega is already used for permutation, so I'm using uppercase U to represent the set. So, but this is also recursive. Now, I know this notation looks really ugly, okay, but there's a reason why it has to be like that. So anyway, the most important part is U of I depends on U of I minus 1. So it is also a recursive definition. I'm not sure how many recursive algorithms you have gone over in CISP430. Because that's going to be helpful, because you have one class that actually has all the practical stuff that you can actually see when the program runs, and you can use a backtrace to figure out how deeply you have performed your recursion. So that really helps, because it is looking at things from a procedural perspective in CISP 430, and then in this class we are looking at things more from the mathematical perspective. But when you look at recursion and then you look at induction, which is something that we haven't talked about yet, those two concepts are closely related. Okay, but in this case, let's check out what omega something with a subscript is representing. So we want to get the notations cleared out first, and then we're going to talk about the definition, and we'll basically do a test run. Okay, I don't think we have enough time today to really do a test run, but we'll see. Okay, we'll see whether we can get to that point or not. Alright, so let's start with the definitions. So let T represent the pool of choices originally presented. In other words, T is the set of outcomes for the first trial. So T0 and T are basically exactly the same thing. I'm just calling it T here because we just start with these elements as our possible outcomes. And then we use omega I with parentheses of T to represent the outcome set of an experiment involving I trials, starting with T as the set of trial outcomes. And in this case, it is also implicit. Well, the previous paragraph already explains that these trials are without replacement. So once you take something out, you do not replace it. It's gone and not available for subsequent trials anymore. Alright, so now we get to this part here, which is the end of this is the base case. Okay, this is not recursive, it is the base case. So what is omega 0? Omega 0 basically is saying I have an experiment, but it has no steps whatsoever. We're not doing a single step. We're not taking anything out of the bag. So even if your bag is not empty, even if it has any number of items, but since you're not taking anything out of it, so when we look at the outcome, the set of all the possible outcomes, it will just be an empty tuple because you have chosen nothing out of it. So the empty tuple is an appropriate representation of the only outcome when you have no steps involved in the experiment. Is that okay? Does everybody understand this? This kind of relates to something that we talked about earlier, except what we talked about earlier also has an empty bag to begin with. This time we have a bag that may or may not be empty, but we are not taking anything out of it. So when I say, hey, show me your results, you go like, okay, this is the result. Is that okay? I can improve the analogy, by the way, to make it even easier to understand. Sort of. Okay, so that means I should improve my analogy. Okay, so imagine this. And whenever we want to imagine something, it helps to draw pictures, right? Okay. So, in this case, I give you a bag of items. Okay. So once again, we can do the alphabet soup thing. So we got A, B, C, and D. Okay, doesn't matter. Okay, the bag can even be empty, but we'll just say that we stuff it with something to begin with. And I'm gonna say, okay, for every experiment, for every instance of an experiment, I want you to arrange the alphabet from the alphabet soup in. I'm trying to find a proper way to itemize the whole thing. So we need to somehow string, the noodles, each noodle, and we want it to be order dependent. So this becomes the difficult part because with alphabet soup, it's harder to do it. So let's not use alphabet soup. Let's use marbles. So we have 4 marbles labeled A, B, C, and D in this case. And I say, after you perform a particular instance of the experiment, I want you to show me a tube where the tube has all of these marbles in it whatever you have chosen in the order that they are chosen. Okay, so that means if you are talking about two steps, okay, m equals to 2, then your end result is going to be a tube where it has A and B in it. If A is the first marble that you drew out of the bag, then A will be the first one in the tube, and then you put B, which is the second marble that you take out of the bag, into the tube. Is that okay? I mean, in other words, we now have a container to contain the items that you have taken out of the bag for each trial. Is that okay? Because that's basically what the tuple is. It's not exactly a stack, but you can look at it as a stack, because a stack has ordering, right? So it will still be it's still okay to use a bag for that purpose. I mean a stack. All right. So now if you think about this one, then you can have B A. Basically, we are repeating everything that we had earlier. Okay, let me go back to that picture. Except all of these are now in a tube. Is that okay? That's all. This is the only addition to the concept that we have already talked about. Is in order, I'm giving you a bunch of tubes. Okay, for every trial. Okay, for every finished instance of the experiment, I'm giving you a tube to contain the marbles that you have taken out of the bag in a specific order. Okay, so given this modified picture in your head, now we're going to say, okay, let me erase what I have here already, and now we're going to say we have 0 trials. Okay, m equals to 0. So what are you going to give me? You're going to give me an empty tube. You basically go like, well, tag, you asked me to not to do anything, so here's the outcome. It is a single empty tube to represent the outcome of permutations. Are we good so far? And this is why omega 0 of any t is just going to be a set of an empty tuple, because you're giving me an empty tube back. All right. So now we're going to say, what about the recursive case? Okay, so the recursive case is defined down here. So it is omega of t is the union of choosing something from t, and that something is used, is put into its own set, and then we have a Cartesian product here, and then we have omega I minus 1. But whatever we put, as the argument to this omega I minus 1 is not t, because remember, once we have chosen e as an element out of t, it is no longer available to further steps, to further trials. So it is no longer available to omega I minus 1, because omega I minus 1 is going to find me all the possible outcomes when we have t minus e as its possible choices, and we're supposed to choose I minus 1 items out of it. So intuitively, does that make sense to you? I'm just looking at the clock. Yeah, we're out of time, so I cannot really do an actual rundown, as an example, with all the actual numbers, permutations, and whatnot. I'll do that next time. Okay, so on Wednesday, I'm going to show you okay, I'm going to write this down on the tablet, so this way there's no way I can forget, right? So on Wednesday, I'm going to show you omega 2 of a set that has, I don't want to do 4 items anymore, because that's just a lot of it's going to use up a lot of time, so we'll just do 3. So we'll have A, B, and C as the original t, available to the first trial, but we are going to have 2 trials in the experiment, and we want to look at the permutations that we can get out of this experiment. So we're going to work this out using the recursive definition on Wednesday. Now, you might want to work on this yourself, okay? Because you can definitely follow the logic. The symbols, okay, the only thing that might be mysterious to you is the big U notation. So the big U notation is basically a loop to perform a bunch of unions. And then E is an element of T is basically how we it's specific to each iteration of the loop, and then the expression that we are unioning with each other is going to be this expression here. So the only notation that we have not talked about is the big U notation, which is basically, the big sigma notation, the big pi notation, except in this case, we are not dealing with numbers. We're not summing, we're not multiplying numbers. This time we are unioning sets. I know the concept sounds strange, but we are just basically having a chain of operators that are linked by items, and they are linking the items that are expressed here. So that's all I can say for now, because we are running out of time. So I will see you guys on Wednesday. I do have office hour right after the lecture, so if you have any questions regarding the material of this class or the homework assignment, I can talk about those during my office hour. Alright, so if there's nothing else, I can stop my screen share and the live stream. Alright, see ya.